We're going to start with section E.1, continuing with our algebra review E before we head on to chapter 4. We're going to talk about linear versus exponential functions, okay? So our objectives are to look at characteristics of linear and exponential functions and then write equations given specific info related to those functions, okay? So just to start us off, okay, our linear function, we kind of already are familiar with that one. That one's our y equals mx plus b. Okay, typically we call this slope-intercept form, right? But this will be the general form that we're going to see for a linear function. Okay, it's going to change a little bit when we get to chapter 4, but it's going to look roughly the same. Okay, same idea with an exponential function. We're going to start off with a really basic form and then add stuff to it when we get to chapter 4. Okay, so for an exponential function, oops, I meant to say function, not form here. Exponential function, we have y is equal to a times b to the x power. Okay, I'm wrapping this b in parentheses to show us that the exponent, the x, is only applied on the b, not both the a and the b. Okay, order of operations, exponents come before multiplication, so I would do the exponent first, and then whatever I get from that, multiply it by a. Okay, some more small vocabulary terms. And actually before even that, just the parts of the linear function, remember this m, that's, we call that the slope, and the b, we call that the y-intercept. Okay, over here for the exponential function, we have new terms. Okay, a, it's going to be something called the initial value. Okay, and you're going to find pretty soon that the a is actually also the y-intercept, and we'll talk about that later. And then b is called the base. And then x has a name as well, it's called the exponent. Okay. Now over here with the linear function, some characteristics about m, the slope. If m is positive, if our slope is positive, right? This is these symbols for saying something is positive because positive numbers are bigger than 0. Then remember we call that increasing. Oops. Okay, and then if m is negative, if it's less than 0, then we call that decreasing. Okay, we have similar things over here for the exponential, but for the exponential, we're going to look at b. Okay, and b, it's going to be a little bit of a different requirement for b. Okay, b, if it's bigger than 1, then we're going to call this exponential growth. And that technically means it's increasing, right? And now if b is not just less than 1, it has to be between 0 and 1. Okay, so 0 less than b less than 1. This is the symbolism for saying b has to be between 0 and 1. We're going to call that decay. Okay, for an exponential function, our base, at least for this class, will never be negative. And so that's why we include this little extra thing that b has to be bigger than 0. Okay, and just a few little pictures just to show you what that means. Increasing, positive slope, it's going upward. Negative slope, decreasing, it's going downward. An exponential function that's growing, exponential growth, we have this kind of curve shape where it starts off kind of small and then blows up eventually. That's our exponential growth. Our exponential decay is backwards. It starts pretty big, but then it kind of gets really, really small as you go onward. They're kind of like flipped versions of each other. Okay, so let's start with an example. All right, so now that we know a little bit more about these types of functions, let's see if we can identify them from a table. Okay, so determine whether the given tables represent a linear or exponential function. Well, how can we tell? Well, exponential, that's a multiplicative growth. We're growing by a multiplicative factor. Whereas linear growth, we're going by like an additive or subtractive factor, right? And so the thing that you're going to want to do is you're going to want to look at consecutive differences, okay? Pretty much you have to try 2 different things, okay? So for example, for part A, looking at the output values, our f of x values in our table, we're going to take consecutive values, and by consecutive, I mean values that are right next to each other, and we're going to divide them, okay? And I would do 5 divided by 1, 25 divided by 5, kind of going backwards, right? So what's 5 divided by 1? That's 5. Okay, 25 divided by 5, that's also 5, etc. The idea is that when you do this division and you get the same number every time, then it's an exponential growth, because what's happening is we're multiplying by the same number every single time, which happens to be 5. 1 times 5, or sorry, 5 times 1 is 5. 5 times 5 is 25. 25 times 5 is 125. 125 times 5 is 625. Okay, and so that's where the idea of doing this division comes from, to see if we're multiplying by the same factor every single time. Okay, and I have to be careful and make sure that in the x column that the increments are all the same. Okay, we wouldn't be allowed to do this if I went 0, 1, 3, 4, 7, 10, like the increment was uneven. But if the increment's the same all the time, then we're allowed to do this. Okay, so because of that, this is exponential. Okay, now if we try the same thing over here, for example, let's do, if we're going to do our consecutive divisions. So if I do 0.375 divided by negative 0.5, if you did it really quickly in your calculator, we end up getting negative 0.75. Okay, so if this was exponential, then this next division that I would do has to be the same. 1.25 divided by 0.375 gives us 3.33 repeating. Okay, so when I do 1.25 divided by 0.375, I don't get the same number. So division doesn't work. What else can we do? The other option is to try subtraction. And in this case, you probably already know then, okay, that means, of course, it's linear, but let's just do it anyway, right? We can find the subtractive differences and see if it's the same all the time, okay? The idea is that when we subtract, we're finding out how much am I adding between all of these values to get to the next one. Okay, that's kind of what we're doing when we do this subtraction. So 3.375 minus, oops, I forgot the negative, negative 0.5. Okay, that becomes addition. When we do that, we get 0.875. Okay, let's hope that the next one's the same. 1.25 minus 0.375. 1.25 minus 0.375. We get the same thing. We get 0.875. Okay, and if you do the rest of them on your own, like if you do the rest of these subtractions, you're gonna get the same difference. Okay, and so that means that then it's linear because it's changing by me adding the same number every single time. Okay, and here this is changing by me multiplying by the same number every time. In this one, it's changing by me adding the same number every time. I'm adding 0.875 every single time. Okay, and so that's how you can tell the difference. Divide the consecutive numbers, and if you get the same number, then it's exponential. Subtract the consecutive numbers. If you get the same number, you get a linear function. Okay? Cool. So now that's how we can determine from a table whether a function is linear or exponential. Okay, are the y values growing by multiplication or addition? And then from there, that'll tell you whether it's exponential or linear. Okay, now let's try writing some equations. All right, we have example 2 here, which is write the equation of the linear functions below. So they give us linear functions in table and ordered pair format, and we want to be able to use this information to write the equation of the function. Okay. So if you remember from the example we just did, a linear function that has the same difference every single time, and we found that difference by subtracting all the consecutive numbers. So if I do 2 minus 5, I get negative 3. And if I do negative 1 minus 2, I get negative 3. So this is going down by 3 every single time. Well, remember, With slope, it's the rise over the run. Notice that my rise, my quote unquote rise, my change in y is -3, whereas my change in x is just 1. Okay, I'm adding 1. So my slope here is actually -3 over 1, or just -3. Now that's kind of the intuitive way of going about it. Another way we can go about it that's a little more maybe you prefer a formula. Remember our slope formula? Y2 minus y1 over x2 minus x1. These are technically ordered pairs. I can technically put these as ordered pairs. I can, wrap, this is 0, 5, 1, 2, 2, -1. If I wanted to find the slope, you can just pick one of these points to be x1, y1, and another point to be x2, y2, and just use that to calculate the slope, and you'll get -3 once again. Okay? So what was the point of finding the slope? Well, our equation is y equals mx plus b. And we're trying to write an equation that looks like this. And so we have it, we're halfway there. We have the slope so far. We just need the y-intercept. Well, what is the y-intercept, right? It's where the line hits the graph. Sorry, it's where the graph of the line hits the y-axis. And at the y-axis, what is our x value? It's 0, right? If I think about my coordinate plane, if I'm at the y-axis, my x value here is always 0. So it's the y value wherever my x value is 0. Do I have an x value of 0 in this table? Yes. 0, comma, 5. So my y-intercept is 5. My equation is y equals -3x plus 5. Okay? So just to recap how we did that, we found our slope. Okay, we have this intuitive way of doing it, but we also can always use the formula. And then we looked to see if we had 0 as one of our x values. And since we did, that corresponding y value is the y-intercept. Okay, let's try it again just to make sure it's clear. Okay, here we have ordered pairs, so maybe it might be helpful to actually use our slope formula to find the slope. Okay, so m, I have 3 points here. I have 3 ordered pairs. I can just pick whichever 2 I want. I'm going to pick this first one, x1, y1, and this second one, x2, y2. So then for my slope, y2 minus y1, that's -1 minus -2 over 0 minus -3. What does that become? 1 minus -2, that's 1 plus 2, -1 plus 2, which is +1, over 0 plus 3, it's 1/3. Okay, so my slope is 1/3, which means I'm almost done with the problem because now my equation is y equals 1/3 x plus whatever my y-intercept is. And look, we did it. We have it again. We have an x value of 0. So that means the corresponding y value is my y-intercept. In this case, it's -1. So then we're done. Y is equal to 1/3 x minus 1. Awesome. Okay, not too bad. We're going to do the similar thing with exponential functions. Okay, in our last example for this video. Write the equation of the exponential functions below. Okay, so in this case, okay, remember our exponential equation, the general form is y is equal to a times b to the x. Okay, our base, as long as my x values are incrementing by 1, our base is going to be whatever multiplication factor I'm using. So what am I multiplying each y value by every single time? Because that number that I'm multiplying by will stay the same always. Okay, I'm always multiplying by the same number in an exponential function, right? So that kind of solves the mystery for B, but what about for A? Well, A, if you kind of remember what I said above, A is also technically in this case, we called it our initial value, but it's also technically the y-intercept, okay? And why is that the case? Well, if I take the equation, remember to find the y-intercept in general in an equation, we plug in 0 for x. So a times b to the 0. If you remember from algebra 2, anything to the 0th power is just 1. So b to the 0 is 1. So a times 1 is just a. So then my y-intercept is always going to be just whatever a is. So then that helps us because just like for example 2, if we have an x value of 0, whatever the corresponding y value is, it's going to be that a value. And then we'll have found both of the constants that we need. Okay, so let's try with part A. We're going to find the consecutive differences. Note that our x is incrementing by 1, so I can safely just assume that whatever my multiplication is here, that's going to be my b. Well, what's 6 divided by 3? That's 2. 12 divided by 6, also 2. Okay, so we know for a fact this is exponential growth. And in this case, that growth factor, that b, is going to be 2. It's whatever we're multiplying by. Okay, as long as our x is going to increment by 1. And we won't really have to worry about if x is incrementing differently, because then in the future we'll have different devices for how to solve that. We'll see a lot of that in chapter 4. Okay. So far my function is y is equal to a times 2 to the x power. Okay, and then notice I have 0 as my x for one of them. The corresponding y value is going to be my y-intercept or my a value. So in this case, my function is 3 times 2 to the x power. Okay, very nice. And if you're ever hesitant, you can always check, okay? When I plug in 0 to this function, do I get 3? Yes, 2 to the 0 is 1, 3 times 1 is 3. When I plug in 1, I get 2 to the first power, which is 2, times 3 is 6, that checks out. When I plug in 2, 2 to the second power is 4, 4 times 3 is 12. Okay, so yeah, my function does work. Awesome. Let's do it one more time. Okay, I got to do my consecutive differences. So I got to do 4.2 divided by 2, and then 8.82 divided by 4.2. So let's start with the first one, 4.2 divided by 2. That one, that looks like it's equal to 2.1, right? Let's just make sure that we get the same thing for the second division. 8.82 divided by 4.2. Okay, 8.82 divided by 4.2. Yep, that's also equal to 2.1. So there's your growth factor, okay? So y is equal to a times 2.1 to the x power. And then again, I have 0 as my x here, so then the corresponding y value is the a, which is 2. So our function is 2 times 2.1 to the x power. And you can confirm for yourself by plugging in all those x values and checking that this is indeed the right function. Okay? So there's E.1, you guys, just a quick little introduction to comparing our linear and exponential functions.